this rank gradient and Heegaard gradient that we talked about last time. So let me just put those definitions back up on the board. So we'll say gamma is a finitely generated group, and then and you have a chain of finite index subgroups, and we define the rank gradient of this chain to be you take the rank of gamma n minus 1, then you divide out by the index, and then you take the limit as n goes to infinity. And we said that this was monotone decreasing, so the limit exists.
Are these gamma individually finite or just some sort of chain?
This is just a chain. I mean, yeah, I'm not requiring it to trivially intersect or anything right now. Yeah, and then if so in the case that gamma is like pi1 of m, say a closed free manifold, then if I have this chain of subgroups here, finite index subgroups, then that determines this a covering tower. Right, so gamma n determines a tower of covers, say m covered by m1 covered by m2, where pi1 of mn is identified with the subgroup gamma n inside of pi1 of m. Okay, and then we define the Heegaard gradient of gamma n to be something similar, but using Heegaard genus instead of rank. So, yeah, I mean it's not like so important. I mean the point of the 2g minus 2 is just to make this sequence monotone decreasing, which I guess is convenient. Then you can say that the limit exists, everything. So I mean it's a convention really. Like you're just saying by convention we put Euler characteristic on the top instead of genus, but it doesn't really matter. Right, and then I guess I ended with this question last time, which was that does there exist such a tower Mn with rank gradient 0 and Heegaard gradient positive? That was sort of the setup from last time. Yeah, okay. So so I think I left you with a dearth of examples at the end of last time. So let's just do one example, say, where we can calculate what the rank gradient is and like the Heegaard gradient. So this is an example of mapping tori. Okay, so I'm going to create a closed 3 manifold for you, and the input data is I need to start with a homeomorphism of a genus G surface. Right. So let's let, as before, sigma G be the closed orientable surface of genus G, and then F from sigma G to itself is a homeomorphism. Okay, and then we set the mapping torus of F to be you take sigma G crossed in interval 0, 1, and then so this is a manifold with boundary, and then I'm going to and the boundary is 2 copies of sigma G, and I'm going to glue them together via F. Okay, so then x0 here gets identified, say, to f of x1. Right, and the way I want you to picture the mapping torus is well, this is of course like an awful picture, but all right. So you've got the surface cross interval, and you glue the ends together. Of course, this picture doesn't capture anything about the map F, which is sort of the crucial input for for the topology here. Okay, so right, so here if I take MF and then I just project onto the second factor, which is an interval with its endpoints identified, then I get a fibration over S1. Okay, so just by projecting onto the second factor, and so that gives you that allows you to represent the fundamental group as like a semi-direct product of pi1 of the surface and Z. Okay, where the z acts on the pi1 of sigma g via the induced pi1 action of f. Yeah. And so in particular from this, like what's the rank of MF? Okay, well, I mean, in general, the rank of MF depends on F, but we can give a nice upper bound. Okay, so here the rank of MF is at most. Well, if I have a semi-direct product like this and I want to generate that group, then it suffices to take generators for pi1 of sigma g and one generator for z, and so you get rank pi1 sigma g plus 1, so that's 2g plus 1. Okay, but it's very possible that the rank could be less. Okay, so these are the sort of obvious generators for pi1 of MF, but maybe there are really mysterious generators that we can't see in this picture. And maybe as an aside, also the Heegaard genus is at most 2g plus 1. Yeah, I guess I can just draw you a Heegaard splitting of this. So I need to divide this thing into two handle bodies somehow. And here's how you do it. So take like two copies of the surface. So this could be like sigma g cross 1/2. And then what I'm going to do is I'm going to take like a tube, so a thickened interval, and I'm going to take everything sort of on this side of those two surfaces except for that thickened tube, and then add into that a thickened tube on the other side. Okay, so the shaded thing here is a handle body, and its complement is, I mean, this picture is sort of symmetric too, so its complement is also a handle body, and if you check the genus here, it's what? It's like this surface has genus G, this one has genus G, so 2G, and then there's one extra genus coming from these tubes. Okay, so what about this rank gradient and Heegaard gradient? Well, the point is that if I have a mapping torus, then there's a natural family of cyclic covers of the mapping torus that I get by just unwrapping the circle direction. Okay, so right. So here, right, if we set like gamma n inside of pi1 of MF to be like pi1 of sigma g semi-direct like nz, then then the associated cover mn. Well, okay, so this is then also going to be a mapping torus of a sigma g surface, but now where the homeomorphism that you use is f to the n. Okay, and the picture you should have in your mind here is like, okay, here's your mapping torus, and then what are you doing? You're just you're taking a cover that looks like this, say, where here n is 3. All right, makes sense so far? Okay, so then what do you get from this? Well, so if you take this tower of covers, or this chain of finite index subgroups, and the rank gradient and the Heegaard gradient are both 0. Right, so rank of MF or MFN, G of MFN are both at most 2G plus 1, and this G is constant. Okay. Hopefully it's not confusing that I'm using G for genus of Heegaard genus here, and also G for the genus of the surface. Those are two different G's. Okay. If I were fancy, I could do. Okay, but both these are bounded, and so that then the rank gradient of of this sequence gamma n, and the Heegaard gradient of this sequence gamma n are both 0. And you know, it's also worth noting here that here here what's the intersection of all the gamma n's? So if I take all these gamma n's and I intersect them, then I get what? So the only thing that's happening here is I'm taking nz instead of z, and so if I intersect them all, I get pi1 of sigma g. And so sometimes, so in a little bit, it'll be necessary for us to talk about, you know, the case that Dave was talking about at the beginning, like sometimes you want to consider not just chains of subgroups, but chains of subgroups with trivial intersection. And this is not an example of that. Okay, so this is not one. However, there exists also chains of subgroups of this pi1 of mf with that do trivially intersect and are even okay. So so the subgroups before were normal. These are also going to be normal. Where the rank gradient and the Heegaard gradient are 0. Okay, and yeah, so how do you make those? Yeah. Was that? Yeah, that's right. Okay, so so how? So here so what you want to do is, like, here you're just keeping the surface fixed and you're just unwrapping the circle direction. So what we do is we just unwrap the surface at the same time as we unwrap the circle direction, but slower. Okay. So right. So really, what we do is we take a chain of normal subgroups with trivial intersection, like delta n inside of pi1 of sigma g, and then you set gamma n to be right. So gamma n is supposed to be then like delta n semi-direct. INZ, where you want IN here now to increase really fast with n. Okay, so then the picture, instead of what's over there, instead of having this picture, now I have some picture where, okay, the fibers are bigger. Like now maybe they're genus 4 surfaces or something. But I've taken the cyclic cover part to be so huge that still the volume of this is much bigger than 2 times whatever this genus is plus 1. Yeah, right. I mean, you have to right. So these are chain of finite index normal subgroups with trivial intersection. So I mean, you're right. Like F might not preserve a particular gamma n that you pick, but then a power. Or rather, it's like, right, F might not preserve a particular gamma n that you pick, but then if you raise it to a power, it will preserve that gamma n. And so, like, right, it's not like I can take any fast increasing sequence here. I just need to take a fast increasing sequence where the appropriate powers of F, preserve these subgroups. Yeah, okay, yeah, you could do that too. Well, no, because you need right, if you just no, because I mean the rank of this gamma n depends on I mean, an upper bound for the rank of gamma n depends on rank of delta n, right? Oh yeah, no, you're right. Yeah. Okay, so yeah, okay, so I think maybe at this point, let me just make a couple of quick remarks, which is that so all this was just 3-manifold topology, but so you can also make this happen in the world of hyperbolic geometry, right? So so Thurston, and I guess the paper is from '86, showed that MF is hyperbolic, so it emits a hyperbolic metric if F is so what's called Souto and Asov, which is a generic condition. Okay, so right, there are hyperbolic mapping tori in particular. And in fact, maybe I should also mention, so this resolution of the virtual fiber conjecture by Ian Nagel, and like using work of Donnie Wise, says that any closed hyperbolic three manifold, say, has a finite cover that that's a mapping torus. Okay, so what about so this gives some examples where the rank gradient and Heegaard gradient are 0. So say you're looking for examples where they're positive. Well, maybe let me just draw you one picture quickly. So there's work of okay, so this is like Du Bois and Du Bois, Friedel, and Vidusi from I think 14. And also maybe I'll cite Lackenby 06. So if you do this sort of the same picture here, I'm going to draw kind of the same picture, except now this is no longer a mapping torus. It's well, it's not a mapping torus. Okay. So what's the content here? This is some pi1 injective embedded surface. So if I have this picture, then I can make cyclic color covers in the same way as the previous picture. So now now the picture looks like okay, well maybe I'll draw it like this. So there's like, okay, this looks like what I drew before, but now each one of these things has a bump. Right. And if you and it turns out that if you do this, and this is not a mapping torus. Okay, so there's actually, this is not like a the complement here isn't that surface cross I. There's some more complicated topology there. Then the rank and the Heegaard gradient are positive. Okay, so this is like, here's your M. Here's your tower of covers Mn, where I unwrap more and more, then the rank and Heegaard gradient are positive.
So you're only unwrapping the direction.
Yeah. No, I'm just unwrapping the Z direction here. I've tried to indicate that by having these still be genus 2, but I didn't write anything, so it's confusing. Yeah. I mean, really, just like these covers that I'm making, it's really just like cut along the surface and then like glue n copies of the result together in a circle. So those are the covers. Mm-hmm. Yeah, non-separating pi1 injective embedded surface. And with the attributions, like Lackenby shows Heegaard gradient is positive, and Du Bois initially did this for hyperbolic manifolds, and then they generalized it to more general three manifolds.
If you had only unwrapped it.
What's up? Like if I, right. So if I only unwrap in the surface direction, I'm not. Yeah, I guess it's not so clear what happens in that case, because I mean, like the obvious generating set has a lot of generators in it, but I'm not sure if there's like some much better one. Well, I mean, nothing in these pictures is totally geodesic. Yeah, and then maybe I should also mention, like, okay, so there's one example that we'll need later too, which is that so again, this chain of subgroups that I'm describing here doesn't trivially intersect, right? Like here actually, like the if you think about it, what's the intersection of all these subgroups? It's like pi1 of the manifold that you get when you concat infinitely many of these like bumpy pieces together. So it's going to be, some infinitely generated group. But it's also, but I also want to give you like, just say that there's an example where the say the Heegaard gradient is positive, and the chain trivial intersects. Okay, and so here's that example. So let's say that M equals H3 mod gamma is a closed arithmetic hyperbolic 3 manifold. Okay, and gamma n is the chain of principal congruent subgroups. Okay, so I mean, right? If you're familiar with the arithmetic language, then that's great. Maybe if not, maybe I'll lie a little bit, but like the picture that you should have in mind is the following. So you think for instance, think that you have some way of taking isom of H3 and taking a representation of it into GLNR. And then you should think of like gamma as like row inverse of GLNZ. I mean, think this if you've never seen any of this before. And then gamma n you want to think of as just the row inverse of like all A in GLNZ that are congruent to 1, are congruent to the identity matrix mod n. Okay. All right. So I mean, it's not quite right, but it's fine. Excellent. Yes. No. Okay. Okay. Good. Well, I mean, this is all I want to say about that for now. So. No, yeah, thank you. All right. We'll break all of this chalk. Okay, so these are like capital N's and this is like little n. Yeah. Okay, so so in this case, then, so I'm not going to say much about this, but let me just say that there's results of Sarnak and Chu from 91, I think, and then if you combine them with results of Lackenby from his 06 paper, then they show that the Heegaard gradient is positive. Okay, but rank gradient, I don't know.
Question
Yeah.
from the chat.
What's up?
Is there a connection between positive rank gradient and virtually surjecting a free group?
Yeah, well, I mean, if you like if you virtually surject onto a free group, then you can construct chains with positive rank gradient, for instance, by you take a chain in the free group and pull it back, and then that gives you a chain with positive rank gradient.
How do you see the Heegaard genus when you have like subgroup? Like algebraically, is that what would be like algebraic analog of the Heegaard genus?
Well, I mean, I don't think it like I mean, the way that this breaks down here is actually that they so they show that that these like the associated covers are expanders, and then the work from Lackenby's work says that if you have an expanding tower of covers, then the Heegaard gradient's positive. So.
In the static thing that we do with the band, can you cut another surface along the band with the band part, and then glue, I don't know, in some take any graph and make a gluing of those things. Make under graph.
Yeah, well, I mean, sure. I mean, you can. Right, you're wanting to say like you want to construct more examples where the rank gradient and Heegaard gradient are positive by instead of having these manifolds that look like you know, like a graph that's a cycle, maybe have a more complicated graph. And yeah, you can totally do that.
And just one more question about that picture. In that picture, maybe an example we should have in mind is the fluidity that thing.
Yeah, in that example, you could have a totally geodesic thing in mind, right? Oh, maybe that's what you were asking earlier. Yeah. Okay. Cool. Sorry. Yeah. All right. So, okay. So I think these are all the examples I want to talk about right now. So I think I'll spend the rest of the time giving like a a short introduction to a different perspective on rank gradient, namely through something called cost. All right, so here's the setup. So let's let gamma be a finitely generated group, and gamma in a chain. Okay, so all right, so I'm going to define something called the coset tree. And so what is this? So I can make a tree, so a rooted tree, by having the vertex set be just all, say, right cosets of the gamma ends. Okay, and where I connect two cosets with an edge if one contains the other. Okay, so it's like, I take gamma ng and then I connect that with an edge to gamma n plus 1, like h, if the first contains the second. So then you get this picture where so the root of the tree is gamma, and then I have like a gamma 1 and all the cosets of gamma 1, and then I have, branching off from that, there's like gamma 2 here and all its cosets, and each one of those, then I have all these cosets and those cosets, et cetera, and then you get this tree. Okay, and so the geometric group theorists in the audience will appreciate that if you have a tree, you can look at its boundary. So we set so here the boundary, you can just describe it as right. So it's just like it's the set of all rays in the tree starting at gamma and going down. So so another way to say this is just it's the set of all chains, gamma containing gamma 1 G1 containing gamma 2 G2 containing et cetera, et cetera. Okay. And visually, you sort of imagine you're supposed to imagine the boundary sort of as this Cantor set at infinity. All right, and then so given so if I give you one of these cosets, so given like gamma n, how about h? So we can define its shadow. So this is shadow of gamma n h. And so this is just so I mean the picture that you should have in mind is like if I have this coset here, then the shadow is like the points in the boundary that are below that. Okay, and how do you make that precise? It's just the shadow is like all chains where the nth term is gamma nh. So coset chains where the nth term is gamma nh, and then this is a subset of the boundary. And then these shadows give you a basis for a topology on the boundary that turns it into a Cantor set. Right, so shadows give a basis for the topology on the boundary, and also they determine a natural probability measure on the boundary. And so we let like mu be the probability measure on the boundary, where mu of the shadow of like some coset is 1 over the index. All right, I mean, so this is this is very visual, right? I mean, you're just saying like if I look at gamma 1, then all its cosets have shadows, and they partition the boundary into a number of pieces that's equal to the index, and I'm just giving each one of those equal weight. All right, so in here, gamma acts on the boundary on the right, say, via automorphisms of this. Okay, so it acts on the tree on the right via automorphisms, and because these automorphisms like preserve height, they preserve they send shadows to height n shadows to height n shadows, and therefore preserve this measure. Yeah. Yeah, I mean, what? So, yeah, say more. Yeah, okay. So, let's see, what are we doing? Oh yeah, okay. So the point is that now I want to try to capture the rank gradient of this sequence gamma n by looking at this action on the boundary of the tree. Okay, so yeah, and to set up some of the language, I'm gonna sort of work a little bit more generally, and then we'll go back to the tree picture in a second. So let's suppose so here's the sort of general setup for defining what's called cost. So let's suppose that X is a some space and okay. So I want some assumptions on this space, but ignore them if they're unfamiliar. So X is some space, and then mu is a Borel probability measure on X. Okay, and then let's suppose that we have a gamma as a countable group that acts on X, preserving the measure. Okay, so I'm gonna write things as right actions here. Preserving the measure. Okay, and so I'll sort of refer to this setup in brief as a PMP action of gamma. So here, PMP means that was like a that was a musical interpretation of descent down the tree. So okay, so this is a PMP action of gamma, where PMP means probability measure preserving. Okay, so you act preserving this probability measure. And so from this setup, I'm going to define for you so this object G. So what's this G? So this is okay, it's just this set of triples, say X comma gamma, or I'm doing right actions, right? So right, so I'm going to write my actions like this, where X is in X and gamma is in gamma, and this is just a subset of X cross gamma. Okay, and how are you supposed to visualize this G? Well, I want you to visualize it as so let's think of elements of G as like directed edges. All right, so directed like gamma labeled edges, where so here I have a point X, and then I have this directed edge that goes from that to gamma X, and the label here is gamma. Okay. Just because I'm wanting to keep track of some additional structure. Like, yeah, I mean, I guess maybe you'll see in a little bit. So yeah, okay. So wait, say again. What? Yeah. Yeah. So yeah. So the point is that this okay. So this G has a composition and inversion operations, right? So so if I have like X and then I have an edge to Y labeled gamma, and then I have an edge from that to Z labeled delta, then because these edges come from a group action, I get a composite edge here that's right, that's labeled gamma delta. Okay. Right. So this is the composition, and then I also have an inversion operation where if I have X and then I have Y here, and this is labeled gamma, then I also have an edge going the other way that's labeled gamma inverse. And so if this terminology is familiar to you, then what I'm saying is that this G is a groupoid. All right. Okay, so if I have this groupoid, so a graphing of G is so it's a subset, maybe I'll call it C inside of G. So it's a Borel subset, C inside of G. I mean, here G sits inside of X cross gamma. So this space has a Borel structure, and so I want C to be Borel in that sense. And so I want this C to generate G as a groupoid. Okay, so that just means that like every element of G is obtained from things in C by compositions and inversions. So okay, so what's an example? So let's say that that gamma is generated by a set S. So then I can make a graphing by just taking C to be the set of all arrows X going to going to X dot S, where X is in X and S is in S. Okay, and then this is I mean, some people call this the Cayley graphing. And maybe as a test case, so if right, if gamma acts on X freely, okay, so I'm not assuming that it acts freely in any of the setup, but if it does act on X freely, then what's a graphing? Well, so if you have a free action, then there's if you have 2 points in the same gamma orbit, there's a unique edge going from one to the other, and so so graphing just needs to connect everything in like each gamma orbit. Okay, so in other words, like a graphing is just a Borel like graph with vertex set X, whose so I mean, I guess the directed graph the way that I'm saying it here, but with vertex set X, whose connected components are the gamma orbits.
It's not free, and you have like million edges going between X and Y. And so if I put only one edge, that's not good enough to be a graphing.
Yeah, maybe not, because you need to. It's like you need to remember more of the group action. Like like in this setup, you could imagine gamma just acting trivially on 1 point space. Right, and then you have and then this G has just like X and then all the different gammas in it, and you need to be able to generate all those different gammas. Okay, so those are some examples. Right, now we can define cost. So definition: if C in G is graphing, let's set like IC of X to be the like number of edges starting at X. So I is like initial. Okay, so I'm just counting the number of edges like X and then going to something.
Including if there are multiple edges with different labels, you count them.
I count them all, yeah. Yeah. So I see of X is that. And then I say, so set the cost of C just to be the integral over X of IC of X d mu. Okay, so this is like the average number of edges coming out from a point in X. Because this mu is a probability measure. And then I can set the cost of the action, or the cost of this measured groupoid, if you prefer, to be the just the inf overall graphing C of the cost of C.
Visualization on one point, and let's say an infinitely generated, not finitely generated group, your cost is infinite.
Yeah.
Oh, okay, so it's very different from the cost I know.
Yeah, I mean, this is a groupoid cost instead of equivalence relation cost. Yeah. But for for essentially free actions, like it's the same thing. Yeah. Which well, maybe let me keep going for now. We can talk just because I want to get to. There's something I actually want to get to by the end, so I don't have to talk about any of this next time. Okay, so so homework, yeah. Ask Dave. Dave is going to be. Okay, so what do we do with this though? So maybe one remark. So if I look at the cost of gamma acting on X, how does this relate to our favorite invariant? Well, it's at most rank gamma. Okay, because you look at this, you look at this Cayley graphing, and then the right this is equal to the cost of the Cayley graphing. Associated to a minimal rank generating set, or a minimal size generating set. Okay, so right, but why am I talking about all this? Okay, maybe that's the question. So the reason I'm talking about this is because there's this great theorem of Miklos Abert and Nikolov from 2009 that says that the rank gradient of gamma n plus 1 is the cost of gamma acting on the boundary of this coset tree. Yeah. Yeah, and what's wonderful about this is that, okay, if you actually once you know this is supposed to be true, like this is not really that hard to prove. It's it's like a page and a half in their paper. So one half you could even sort of do as an exercise if you, homework. But yeah, there's like no assumptions on the chain here really. Like it's so the gamma action maybe is not free.
Chain exactly applicable. The chain, it depends whether the chain that is intersecting is applicable. The intersection of the chain.
Yeah.
It's trivial.
Well, what are you saying that what are you saying depends on that?
If it's intersectionality, then the action is free.
Oh yeah. No, sorry. Yeah, I missed the first part of that. Yeah, I mean, right. If it's a normal chain. Okay. So right. So what do we do with this though? So yeah, what do we do with this? Where do I want to go with this? Groupoid cost. Yeah. Yeah, that's sort of why I'm phrasing it this way. Yeah, it's because like take the Cayley graphing associated to that generating set, to a minimal size generating set, then the cost of that is exactly the rank. Like track through the cost, and like you see, like the number of edges coming out of anything is like exactly the number of generators that you're using. So this I of C is exactly rank, and then you're integrating that over a probability space. Yeah, I mean, you get a different Cayley graphing for different x's.
So regardless of whether you land at the same point or not, because that many labeled edges coming out of the first.
Yeah. Yeah, come talk to me. Like, yeah. So what's the end of this story though? So okay. So the end of this story is that so definition. So a group gamma has a fixed price C if cost of gamma of any action is C, for any probability measure preserving, let's say, free action of gamma. Okay. And there are a few examples of groups with fixed price. So Fn has fixed price n. It turns out this is a theorem of Gaboriau from 2000, just as one example. And then there are lots of other examples like infinite amenable groups. Yeah, and one of our audience members, and so Sam Melick in joint work with Amanda Wilkins and Mikolaj Fracik, so they recently showed that higher lattices and higher rank simple Lie groups have fixed price 1, for instance. But what's sort of amazing is that there's this I guess the fixed price conjecture is, well, every countable gamma has fixed price. I guess this was initially posed as a question by Gaboriau, but I don't know, people refer to it this way. Yeah. And so the connection to three manifolds that I wanted to talk about is just that, well, so there's a what can you get out of rank gradient here? Well, so as a remark, so if gamma has fixed price, then the Abert and Nikolov theorem imply that if you take any chain, right, so for any chain gamma n of normal subgroups with trivial intersection, so the action of then as Uri was saying, that like the action on the boundary is free. Then the rank gradient is always just this is like C minus 1. Okay, so it doesn't depend on the chain that you pick. And so then using this, they prove the following theorem. So if the fixed price conjecture holds, then there exists a hyperbolic 3 manifold M and a tower of covers Mn with rank gradient 0 and Heegaard gradient positive. And this is like a 2-line proof given what we did earlier. Because what is it? You just say, okay, so take a M arithmetic, and then Mn the tower of congruence covers that we talked about earlier. So the Heegaard gradient is positive. And then you just say, well, okay, I don't know how to calculate rank gradient of that chain, But I know how to calculate rank gradient of a different chain, namely the one coming from mapping tori. So since M has a finite index, or a finite degree cover, that's a mapping torus. It also has a normal chain with trivial intersection that has a rank gradient 0. So that means that rank gradient of our MN is 0 by the fixed price. All right, that's all.
Any quick question?
Ah. I'm totally not qualified to answer that. I'm gonna go agnostic. I mean, I think there are people in this room that are more qualified to. You believe it? Okay.
Fixed price conjecture, just need fixed price for hyperbolic lattices, right?
Yeah, right. I mean, you need fixed price for like that hyperbolic lattice.
And that starts to be more predictable.
Yeah.
That's kind of like all things that I have to think.
Yeah, I mean, equivalent. I mean, yeah, if it has fixed price, then all the rank gradients of these kind of chains are the same. But yeah, no, you need something much weaker than actual fixed price to do this even. Yeah, I guess right. I mean, really, you need something like multiplicativity of cost under finite index subgroups or something, which is like a weaker conjecture even. Yeah, I mean, you need it for this one lattice. If you're arithmetic in a mapping torus, then you're I don't know. I would have to think about that. Like if you take the congruent subgroups, then do they all map surjectively onto Z? If you have a mapping torus. What's up? Okay. Oh, okay. Right. Yeah. Yeah. Yeah, right.
And what is known about lattices and Lie groups? They all have fixed price.
Okay.
In which sense?
Lattices in higher rank simple Lie groups have fixed price one. For instance, there's other statements as well.
But not for lattices in F1.
Yeah, right. Yeah. I mean, you know how, right, you understand them in H2, but but
Wait, there is no more question. Then thank you again. And we resume at 11.